Hi, let's solve this question together. In an aqueous solution, classify these compounds as strong acid, weak acid, strong bases, weak bases, or other. Okay, so what does it mean by others here? Other here should mean that some neutral solution when the pH equals to 7. And if the solution has a pH greater than 7, it means that it has released a lot of hydroxide group -1, then it should be a base, and the rest, if it has a pH less than 7, it means it's releasing a lot of proton H+, then it should be an acid. Okay, let's check out the first one, BaOH2. So we can see it have a hydroxide in the molecule itself, and Ba is a barium. So this is a barium hydroxide, and barium is a alkali earth metal. So whenever you see a hydroxide from a alkali earth metal, then it should be a really strong base, okay? Or if it's a alkali metal, it's also a strong base as well. So let me move it here. This is a strong base. So let's just have a look. Oh yeah, we also have this one here. You can see that this is lithium, lithium hydroxide, and lithium is a alkali metal. So that's why this one is also a strong base as well. Okay, so I will move it here to the strong base. Okay, so now let's check the next substance here, CH₃COOH. So I got a structure here. You can see that the first C is actually bond with 3 other hydrogen atom, and that it will bond with another C. The second C will have a double bond with another oxygen, and it will bond with another oxygen. And then the oxygen, that oxygen also have another bond with a last hydrogen. So you can see that from the name is an acetic acid. Okay, so it's an acid, and actually is a weak acid. It's an organic weak acid. Okay, and why is an acid? Why? Because we seems like we have an OH groups here, right? So why is not a base? Okay, because here you can see there's a lone pairs here, another lone pairs here. So we have the 2 lone pairs on this oxygen atom. Also the same with the 2 lone pairs here on this oxygen atom. And because oxygen atom itself is more electronegative compared to the carbon, that's why it will draw the electron towards it. And if it draw more electron towards it, it just automatically become more negative here, and it will leave the carbon to be more positive charge here. And in order to make up for the positive charge here, it will draw the electron from this oxygen towards this carbon. And then that's why in the end, it leaves like a positive here for this oxygen here. So if you have a look at the electron density map of this structure, you can see here, this is the carbon C, the first one. This is like the 3 hydrogen here, right? This is the carbon here. This is the 3 hydrogen here. Then you can see this is the second carbon. This is the oxygen here, which have like a really negative cloud here. More red means like more negative. Okay, this is a really rich electron zone, and you can see that the blue zone here is a poor electron zone, because the oxygen here, this is the other oxygen here. Okay, it will have like more positive here. So that's why you can see that this zone is like poor electron, which also means that the bond between the oxygen here and the hydrogen here is really a weak bond. Okay, it's a really weak bond. and it means that this hydrogen have a tendency to dissociate from the rest of the molecule. And that's why acetic acid have the tendency to donate the proton, okay? And that's why it's an acid, okay? So if you have a look at these really quickly, these are just like a summary how you can identify if a substance have more acidity or more basic, depends on its chemical structure. If the bond holding the proton, the hydrogen, is a weak one, then the proton have the tendency to dissociate from the structure. Okay, so let me move it here. The conclusion for acetic acid is that it's a weak acid. Okay, it's an organic weak acid. Let me move it here.